Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode, we're gonna take a closer look at spacesuits. So let's dive right into it. Now, first thing you have to understand, why the heck do we need spacesuit? Now, there are five core reasons why do we need spacesuit. First, we need oxygen to breathe. Unfortunately, vacuum does not agree with our lungs, so we need oxygen to breathe. Then we need pressure to operate. Now, this is a very critical part. Human body will not explode, quote unquote. All it will do, it will swell up. We had accident with humans in vacuum chambers where we were testing suits and all that, so we know what happens to a person in a vacuum. You're not gonna explode. You will swell up like a muscular person because your muscle fibers will start to expand. Now, would your basically blood boil? No, simply because your body, basically skin itself, is keeping you under pressure. Now, how much pressure do we need to keep us alive? It's not atmospheric pressure. It's much lower than that. Basically, of course, atmospheric pressure, awesome, but you don't have to have complete atmospheric pressure. So we need pressure to operate. Then we need constant temperature. Of course, our body is an engine. Basically, it's a metabolizing the food that we eat and running our brain, running everything. So it does need a constant temperature. We do not have large temperature range where we can operate. Then radiation shielding, because basically Earth have all of these five things simply because it has an atmosphere. Now, atmosphere gives us pressure, atmosphere gives us oxygen, atmosphere make sure acts as a thermal buffer. Atmosphere also shields us against radiation, because in space there is nothing between radiation from the sun or from deep space to you. Like, it will directly hit you, and that will cause mutation if you are lucky. Worst case scenario, it will flat out kill you. So radiation, we need shielding against radiation. Then micrometeorite. Now again, a spacesuit cannot practically protect you against giant asteroid. That's just stupid. But micrometeorite, especially in low Earth orbit, you can see, like, this is a multi-inch thick aluminum sheet, armor grade, not like a small cheap grade, armor grade, but it can be almost destroyed by a steel wall, like traveling at 28,000 km/h. So that is why ISS has like armor on top of armor to make sure this does not happen. So your spacesuit must protect against something small. Now, of course, it is like, if let's say a wrench is traveling at orbital speed, yeah, your suit is not but let's say plane flake, small nut bolts, those things your suit should protect you. Radiation protection, basically everything our atmosphere does, the suit should also do. Basically, it's called miniature spaceship. So first we come to the most interesting part, the most commonly known part. We need air pressure. Now, the reason you have to understand is that our body is immune to pressure. Like, it's used for its pressure system. So that's why our liquid management, basically like blood in your system, saliva in your mouth, all those things, they expect certain kind of pressure. Like, they are used for Earth environment. We evolve here, so we know how to handle this. However, when you are talking about space or even high altitude plane, this balance goes out of whack. We need pressure. Now, thankfully, we don't need too much pressure. We generally utilize 4.7 psi. Now, if you are familiar with basically sea level air pressure, it's 15 psi, but we can easily, comfortably work at 4.7. Now, benefit of this is that we can breathe in pure oxygen. Now, this is the aspect that you have to understand very thoroughly. The reason why we go through all this trouble rather than just making a suit that literally acts or works like a normal suit is simply because everything leaks. When you are in atmosphere, you don't have to worry about it. Your jet engines, like in a fighter jet that is going very high altitude, it is sucking in air directly from the atmosphere. Of course, it's way too light for our lungs to do, but jet engine is like, I got this. When you are in space, if you are leaking even like, let's say, a few milligrams per hour, your suit is going to become useless. In like, basically you're going to suffocate in your own suit. So that is why people want to keep the pressure low. This is the first thing you learn about whenever you are designing something like let's say for space or something with pressure. Everything leaks. Everything leaks. No matter what you do, no matter how good your engineering, it leaks, especially if it has moving parts. There is a moving human inside, so we have to find a way to make sure the suit does not become useless in after 1 or 2 wearing. So the easiest way is to reduce pressure. Now, if you reduce pressure and you were like, okay, let's reduce the pressure and make you breathe, let's say, low pressure air, you can't do that because there is nitrogen into it, and your lung is expecting a certain amount of oxygen pressure, not air pressure, oxygen pressure. That's why we can breathe pure oxygen if you remove nitrogen from it. So if you want to breathe like air mixture at 4 psi, you're gonna suffocate. That happens to people when they go up to Mount Everest. But if you are if you have air pressure but it is very low, you can breathe in pure oxygen. So if you want to just survive in space, you can literally take in pure oxygen. However, one thing which is like frustrated me when I was watching the movie Gravity is like, the female actress comes in, changes the spacesuit. Yes, she did, Like the moment she did this, she did simply because our real, quote unquote, actual real life spacesuit, because they are at pure oxygen, and environment inside ISS is not pure oxygen, they have to go through what we call pre-breathing. Because I told you, like human body is like completely equilibrium with its atmosphere. So if you want to go to in a scenario where you're like, okay, I'm gonna breathe pure oxygen now, you have to purge your body from nitrogen. You have to make sure you no longer have nitrogen, so you will slowly start breathing slowly. You can't just go attack, you're gonna die. And we learned this the hard way, because a lot of basically scuba divers have died because of this. We call it nitrogen poisoning, because nitrogen compresses at a different rate. In sea it also causes the issue. However, in when you're talking about like spacesuit and all that, there is still issue. It's not that high pressure issue, it's a low pressure issue. But again, you have to understand, nitrogen is very deadly in this sort of scenario. Again, if your spacesuit has exactly the same air pressure, it has to maintain the basically same concentration as inside the ISS. It has to work at 7 psi, because you have to understand, like we are still comfortable inside an aeroplane even though it has lower pressure. 7 psi is like generally agreed upon, like 7 to 8 psi we can manage without like passing out. So they have to always balance things out. They can make a suit that easily work at 8 psi, but it will leak more. They can make a suit that works at 15 psi, no pre-breathing needed, like you just put it on and run away, how they show in movie. But again, it will leak much more faster. So all things combined, they wanted to reduce the pressure as low as possible. And there is another aspect, because if you increase 15 psi inside it, yes, you don't have to worry about breathing, and you don't have to do pre-breathing, you don't have to worry about nitrogen ever. But this will become like a football. Basically, you will be like this, stuck like this. You won't be able to move your hands. Like just try to imagine how hard it is to compress a ball. Now you are inside that wall trying to manipulate things outside. It simply will not work. So that is why PSI has to be kept as low as possible. So 4.7 is like right now agreed upon. 4.7 pure oxygen, and you have to do pre-breathing, because if you directly went like how she did in gravity, she did. There is no talking about, like you did. So air pressure is a very tricky thing. Like people have to spend time to figure it out. Then we come to thermal management. Now vacuum has nothing in it. That's why we call it vacuum. That consequence of that, there is no thermal buffer in it. So basically temperature range can be so extreme. If let's say you have a hand and during daytime you just basically made your hand exposed to the sun, this side will burn, this side will have freeze. Basically, like literally you will have hypothermia on half side and third degree burn on the first side, because the temperature range is that extreme, because there is no atmosphere to buffer it out. So low side can go minus 156 degrees Celsius, and hot side can go up to 120 degrees Celsius, and it can go extreme and all that. However, you have to understand the extreme only happens basically because of sun. So if you go to Mars, the cold side will go only to absolute zero, but hot side will not go as hot as this. It will only go to like 70 degrees Celsius, because it's far from. And if you are like on Pluto, the temperature range will be like more or less absolute zero, because like only radiation is the way to conduct heat. Only solar radiation is the primary reason of heat. So when we are talking about low Earth orbit, you have to figure out how to manage this like upwards of 300 degrees Celsius range. So the only way we can do that is we don't fight it. We don't like, okay, we're gonna cool you or heat you. We don't do that. Many people say that that's what space would. No, they don't do that. You can't do that. So what we do is simply say, let's insulate it. Basically, they have layer upon layer upon layer upon layer up as time like as many as 6 to 18 layers to make sure that there is no temperature fluctuation on the other side of the insulation. Insulation works in both way. Now you created an insulator that can provide insulation against 300 degree fluctuation. How we can we do that? Simply because there is no atmosphere. So like if you took a space suit like something like this, the suit that we use on basically ISS or in space or Apollo missions, that will not work basically in IO or any place where it has atmosphere, because atmosphere will zap things away. But against radiation, insulation works very well. So using that insulation, we shield our astronaut. It's like, okay, the space temperature variation will not touch you. Okay, awesome. But here's the deal: you're gonna kill the astronaut using heat exhaustion, because our body is a machine. It is burning fuel, it is burning the food you ate, and it's producing waste heat. That heat has to be dissipated. That's why you breathe. Like when you breathe out, your basically body is using your air as a regulation, like how dogs do that. And if that is not enough, you will start sweating. So we have many ways to control our internal core temperature. If you don't do that, you're gonna die. Now of course it's not like you're gonna catch on fire or burn like a car engine will, but we're gonna die. So to maintain that, because now you are insulated, you created a scenario where you have no way to dump heat, we utilize liquid flows. Now this garment is the sub-garment. Basically this is not the spacesuit, this is the sub-garment inside the suit, and this has liquid flow into it. Now this liquid has to take care of your body heat. Thankfully human body is not a very hot item. It's only like 100 watt of heating element. So cooling system that you see the big packs on the behind, that only has to take care of 100 watts of basically heat. Sometimes they flat out circulate the water, let it go into space and freeze up. Sometimes they like literally have a cold water that acts as a like thermal battery. It's like it's cold, it will, once it start to reach up in a certain temperature where it's unsafe, they will say okay, your suit has been exhausted, please come inside and change the system. So we need cooling, otherwise you're gonna kill the person inside, not because of space but because of heat exhaustion. So we need seriously complex thermal management. And all this, the temperature regulation, all of the air regulation requires a lot of power. Like sometimes power banks in basically space suits are like 300 watts. So you have to understand, we have to first remove CO2, because CO2 is very deadly. At 11% you will start acting like you have headaches, like lightheaded and all that. At 13% you're dead. At 15% you are guaranteed dead, like nobody will able to revive you. So we have to make sure, even if you have clean oxygen supply, you have to make sure you're CO2, removing the CO2. So first thing is first that CO2 remover, then we supply oxygen. So because even though suit is like a big air balloon, it does not have enough volume to keep supplying oxygen permanently for a very long time. So we have oxygen supply. Then we have a lot of water pumps, water circulation, radiators and all that to manage your thermal properties. And it also includes odor remover, because you are in a concealed environment, your sweat will start smelling like a very bad thing. So there is a lot of odor management done into this. Then it has communication. Now that's absolutely, because you in space you can't yell, so you have to have communication system. And communication system is not limited to just basically talking to one another. It's there are many things about it, like your heart rate, your blood pressure, as many things as they can monitor, they will monitor it and send the telemetry data. So there is a big bandwidth between spacesuit and whatever receiving it. It could be ground station, it could be the ISS itself. So there is a lot of communication requirement also. And then absolutely there would be backup of that, because there are many things which are like built for 6 hours, and there is backup equipment that is built for let's say 30 minutes. So like if your primary fails, you will have 30 minutes to figure what you have to do, like get inside basically in case of ISS. So as you can see, like this is giant complex diagram. You have to understand, this is the expensive part. In spacesuit, everything else is like just fancy material like Kevlar or Mylar for insulation and all that. Those are material, those are bulk buy. You can buy them in like tons and reduce the price. However, this requires a lot of serious consideration. Like this is the engineering part. This is the part where somebody has to, this is something that you can barely do at home. Can you do it? Of course, if you have engineering degree, yes, but this is the part that you have to really spend time on. Everything else is like brute force, like, oh, air is leaking, tape something up, it will work. But again, when you have to talk about like how to manage the thermals, how to manage the communication and all that, and make sure all of that is done with a battery pack that is on the system. You don't have the luxury of umbilical cord. We stopped using that. So you have to understand, these things becomes ludicrously power hungry. Then we come to the problem aspect of it. Now, at this point in time, they are ludicrously expensive. The cheapest spacesuit price that I could find, the actual used one, is $5 million. It can go upwards of $50 million. And the second aspect of it, it's all custom fit. Basically, if you see spacesuits that have like a nameplate on them, there is a reason for that. That nameplate will barely fit someone else. Because like they find your height, they will custom make it. Now, generally they do laser body scan to figure it out. Now, that makes it very expensive. Like every suit is like one of its a kind. So if in emergency they can utilize others, but they won't be comfortable because their joints placement will be completely off. Now of course, height variation in astronauts are generally limited, but it still could be a very big trouble, very expensive. And in terms of weight, because I told you, like suit itself is nothing more than a basic bulky sweater, but the pumping mechanism, all that, everything combined ends up weighting upwards of 150 kilos. Basically, it's more than one person you are carrying. It's like every space suit that you have to carry, you have to like, okay, your rocket is basically carrying one more person, 150 kilos. And it's very hard to use. Basically, flat out, you can't put children inside it. Like, and I'm talking about children, I'm talking about like 10 years old, 12 years old. They will get exhausted very quickly, simply because I told you, like you are working from inside of a basically football. You have to like move things around. It's very difficult. Adam Savage built a basically small test rig to actually see how difficult it is. Basically, he made a vacuum chamber and had a hand grip in it. It's very difficult, and that's why you will hear people say like astronauts have very firm grip, and you will never see a fat astronaut, simply because like if you went inside this fat, first of all, I'm pretty sure NASA will not give you a spacesuit that is like designed to accommodate it, because your heat output will be higher. So let's say you went inside, is working inside like 6 hour or 7 hour spacewalk, yeah, like you would have burned through so much calories, like yeah, you're gonna come out with just a skin, your fat would be burnt out. So it is a very problematic thing. Like if you want to truly do space colonization, we have to solve this issue. It cannot be like freaking more expensive than a Ferrari. It cannot be like 150 kilo that like carrying it, like 2-3 extra spacesuit, most rocket will fail, because like it will mess up their weight capacity. Of course not in space shuttle, because space shuttle had 30 tons of capacity, but yet when you're talking about small rockets, so you have to understand we have a lot of things to fix in this. It does work, it does cost a lot of money, but we really need to push it. Basically it's like 2G in technology, we need to 3G and 4G technology. So this was my presentation about spacesuit. I hope you liked it, learned from it. In that case, please click the like button. If you didn't like it, hated it, please click the dislike button. I would urge you to press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching. And you can also watch my other videos.